All right, so a couple people were asking questions about the homework. I got one on via email that I didn't have a chance to answer, so I thought I'd answer it today. So problem 1.4. So the airplane is not rotating. Omega is 0, which also means omega dot is 0. Because if omega dot is not 0, then omega won't stay 0, right? It will change away from 0. Equations 119 and 125. Yeah. Problem 1.5, the question about the vertical plane. So they're talking about the XZ plane, up and down. And so the airplane can go up and down, it can go forward and back, and it can pitch in that plane. But motion out, like the nose going out of that plane, no. The wings, that's a motion out of the plane, you can't do that. So does that help with that one? I'm going to leave you to interpret that, but you cannot move out of that vertical plane. Yeah. So does that make a part of the airplane move out of the plane? So it's only motion, like it's restricted to a picture of the airplane drawn on the board, and it can only move inside this plane, in this two-dimensional plane. Yeah, so think about it. Is the rotation changing the projection on this plane? Right? If I rotate my hand like that, it's going to change the projection of my hand in that plane. Not airplane, right? Not airplane, but vertical plane, the XZ plane. All right, does that help? I'm not going to give you the answers. You got to figure it out. And 1.9, assumptions made about the linear or angular velocities. So it's a bullet. So think about the motion that the bullet can make. Can it roll? Can it tumble? Well, yeah, I mean, you rifle the bullet in the barrel, right, to keep it stable this way, but bullets eventually do tumble. So, all right, so those are the questions I got emailed. Anybody have other ones? Does that help with those problems? We're good? It's a bullet coming out of a gun. So whatever motion it can make. It can roll, right? It can flip. It can flip all kinds of ways. Yeah. It can't what? Sounds like it, doesn't it? Yeah. If you're still stuck, come and see me tomorrow. Okay? You're going to see me a lot of times this semester? Good, I'm lonely in my office. Okay, so we were finishing up the equations of motion, and we defined Euler angles so that we could talk about the orientation of the airplane in the body fixed axis versus the earth fixed. And in the equations of motion, we have the force due to gravity. So we need to represent the gravity vector, which we know in the earth fixed axis, K1, that's before we do the theta and the psi, well, the psi and the theta and the bank rotations, right? So we're Earth fixed axis here. We translate it to match where the airplane actually is, but we have rotated. And then we do a psi, theta, and phi to get to the body fixed. Well, this is before any of those rotations. So this is an Earth fixed. And so we need to take that vector and send it through those rotations to figure out what it is in the body fixed axis system. Because if our airplane's like that, then gravity's acting in that direction. If the airplane's like this, I mean that banked completely, then gravity's in that direction, right? Different in the body fixed axis, but in the same direction in the Earth fixed axis. So we need to figure that out. So we're going to take the gravity vector in the Earth fixed axis, and then we have to transform it through psi and have abbreviated sine and cosine with a C and an S. So that's the transformation through psi. And then we have to do theta. And then we do phi. Somebody check, do I have a minus sign in each of the matrices on a sine term? And that's going to give us the Earth or the body fixed. And in fact, this vector is what we need to put into the equation. Like that, right? So you guys do this. In fact, I'm going to make it easy on you. I'm going to do the first multiplication. I'm going to multiply this times this because it's easy, right? 0, 0 multiplies that. 0, 0 multiplies that. 0, 0. So all you really get is g times 1. So you can knock that out and you're still left with that. Okay, so I did the easy one for you. So now go ahead and multiply the vector times the matrix on your piece of paper. Get you engaged. And then you're going to end up where you have to do another multiplication times this. So let me make sure I've got it set up right. Okay, looks good to me. So have you guys done the first one? Right, you're gonna take this times this, you're gonna get a vector here. So double check, you should have got this. Check. And this next one is not even hard. You're gonna take this times 1. You're gonna have this times that and times that, because you got a 0 there and you got zeros in the first column. So I'm gonna write this out now. G All right, so once we get that gravity vector, then we stuff it back into the equations we had before. And we get this set of equations that's on the screen. So the top 3 equations are labeled. They're the force along the x-axis. So these are the 3 force equations. Again, you can identify them easily because u dot means it's in the x direction, v dot, w dot, y and z direction. Here's the gravity components that we just plugged in. This is equation 1.51 in your book. It's a summary of the equations of motion. And so we've added this. The rest of this we already had. Here's the rolling, pitching, and yawing moment equations. You can identify those. Oh, this has a p dot and an r dot. But the IXX is a principal moment of inertia. So this is the roll equation for p dot. And this is a cross product, so it's usually a lot smaller, that IXZ. In fact, some of these cross products will drop out if we say the airplane's symmetrical about the XZ plane. This is obviously the pitching moment equation because there's the IYY, and the yawing moment equation because there's the IZZ. And then these equations are the ones that we did last time, and you're actually finishing up for homework. It's the relationship between P, Q, and R, and psi dot, theta dot, and phi dot. So those are called the kinematic equations. All right, so how many equations do we have? 9, that's an easy question, right? There's 9 equations. How many unknowns? These meaning dynamic motion variables. Is M unknown? Mass of the airplane? Is that a dynamic variable? Is it changing with time? No, we assume that it's a rigid body, it doesn't change with time, right? So how about U, V, and W? Those are the velocities, right? So those are unknowns. P, Q, and R, 3 more unknowns. Inside these forces, like FAZ, that's the aerodynamic Z force, we're gonna have lift. And so alpha will be in there, but we know alpha is related to the velocities, right? And so these terms here will contain some of the unknown variables, but they will be related to P, Q, and R, and U, W, and V. And then here, it looks like we need theta and phi for the gravity terms. And so we'll need some of these equations down here. So we have psi, theta, and phi. So we actually have 9 unknowns. See how well I can write. So we have enough equations and we have enough unknowns, so can we solve them? They're differential equations. Piece of cake, right? Differentially, in fact, they're ordinary differential equations. Here's du by dt, dv by dt, dw by dt. The problem is we've got v times r, and that's a product of 2 motion variables. Same thing for w times p, and all the others I'm not going to circle. Here we got p times q, p times r. Those are called nonlinear terms because it's not a number times a variable, it's a variable times a variable. And we talked about this in 514. You can't Laplace those kind of terms. Laplace transforms only work on linear terms. And so just like in 514, we're going to linearize these equations of motion. These are nonlinear. They're hard to solve. Not only that, but we have sines and cosines. Those are definitely nonlinear as well. All right, so the next steps that we're going to take is we're going to talk about what are called the steady state equations, where there's no acceleration. So we're talking about like a cruise flight condition or a steady state turn, no accelerations. But it's still important to analyze that. And then we'll talk about the small perturbation equations that we can Laplace transform and we can do dynamics on. So steady state equations are one of the sets of equations that we're going to analyze in this class. And then the small perturbation equations. So we're going to analyze both of those. So first, steady state. So in the steady state side, in the body fixed axis, because that's what we're working in, all of the UVW, PQR, it's all body fixed stuff. We're going to say the accelerations are all 0. So VP dot is 0. So U dot, V dot, W dot, all 0. Angular accelerations are 0. It's because it's steady state. It's constant velocities, constant angular velocities. So all of those are 0. So that's the steady state equations. And then the small perturbations is we say we have small perturbations on steady state flight. All right, so far so good. You guys have seen this before. We're just going to go through it again in detail, but not belabor it as much as we did in 514 because you know it already, right? All right, but before we get into that, I want to talk about, well, another method for solving those full set of nonlinear equations. So I'll give you a minute to finish writing down what you want to write down here. So the full nonlinear 6th degree of freedom equations, those 9 equations, we can't solve them with Laplace, but we can numerically solve them. We can integrate them in a numerical method. I'll show you how that works. We're not going to go through all the details, but I'll show you how it works on one of the equations. And then it's obvious how you do it for all of them. And this is how a flight simulator works. X-plane, behind the scenes, it has those full equations of motion. And then it has a really good model for the aerodynamic forces and moments and thrust forces and moments, all behind the scenes, and it integrates it in real time as you fly the flight simulator. So we're going to solve them numerically because we can't Laplace. They're nonlinear, makes it hard. So instead of jumping straight into all 9 of those equations, let's just talk about a real simple equation. So we have a mass, and we apply a force that's a function of time, and then we want to track its position. Simple, right? I see you found the plugins, right? Now there's places you can plug stuff in all along each of the tables here. All right, so Newton's law. It's real simple for that mass. And the way we will deal with this is we'll integrate it numerically, is we'll approximate the derivative over a small time step. Right, in the limit, as delta t gets small, we get the derivative. And so if we solve for v 1 time step ahead plus delta t, this says if we know our current velocity and we know how hard we're pushing on the mass, we ought to be able to predict the velocity delta t like 1 second in the future. Makes sense, right? Let's imagine our mass is sitting still, frictionless surface, and we push on it with 1 pound. Over 1 second, that provides an acceleration. If it's 1 kilogram, then we get 1 meter per second of acceleration. So, 1 meter per second squared, which means over 1 second, it jumps up by 1 meter per second. So we can predict the new velocity at the next time step. And we can do this every time step. We can even change the force because we do 1 time step with the current force, the next time step with another force as it changes. And this is essentially numerical integration here. We can solve this differential equation knowing an initial condition at time 0. And we could even, you could do this by hand with your calculator or with a computer. So we start out at time 0 at our velocity v0. And then we go ahead 0.1 second. We're going to do this at a small time step. We apply our force, time step divided by mass, add it to the velocity, and then that gives us our new velocity. And you keep doing that at every time step, marching forward. Sorry, this should be a b at 1. And that's numerical integration. And you can do this without a computer, right? You could calculate this. You know your initial velocity in 1/10 of a second. The force divided by the mass times the delta t gives you the new velocity. So you can do this with each one of those equations in motion. For an airplane, right? They're no different. They're a dynamic equation. Like the u dot equation, there's nothing new there with what we just did. So there's our equation. Let's draw a line to separate this. So we difference this thing. We approximate this by so there's our derivative. We evaluate each one of these terms at the current time. So write a t in there. So we know our current velocity, yaw rate, vertical velocity, pitch rate. We know our current angle here. And we'd have to calculate our forces and moments based on the angle of attack, the current angle of attack, current side slip angle, everything else related there. And then we can solve for u plus t at delta t, so we get our new velocity by knowing our current velocity and all the other stuff at the current time. So there's the first equation of our numerical integration of our equations of motion. You know your current velocity, you know your current angular rates and linear rates, you know your current angle, you know the current aerodynamics and thrust forces, and you get your new velocity here. So you do this for all 9 equations. So you need a pretty decent computer to do this in real time as somebody flies, because when they're flying, the elevator, rudder, ailerons, those go into these forces and moments over here, and that affects the motion of the aircraft. So here I said, well, let's use a time step of 0.1. To do that for this set of equations, you really need a very small time step. Because as you can imagine, look at this, we're using an approximation for the derivative, right? So the first time step, we're going to be a little bit off by the velocity. but we're going to use that velocity again down here. So, and then the approximation here is going to make the velocity even a little bit more off, and so the error builds up. So you've got to make that approximation pretty good if you're going to march forward in your simulation for even like 10 minutes. This is called a first order integration method. And it turns out that for aircraft flight dynamics, that's not good enough, because you have to use such a small time step that to try to do this in real time, the computer can't keep up. And so there are other numerical methods that people have developed to do this. In fact, they were developed even before computers, because people did this by hand. And the one that's usually used for airplane integration is fourth order Runge Kata, and it's a powerful method that actually does 4 steps forward in predicting and correcting itself to even get just one integration time step. And this kind of integration method is done so often that it's built into MATLAB. So you can go into MATLAB and put any nonlinear equation, dynamic equation in there, set it up and tell it to integrate it, and it will. And other packages will do that as well. In fact, this is done for the airplane flight dynamics so much that somebody in MATLAB developed a block in MATLAB Simulink that does the aircraft equations of motion for you. I know you guys know MATLAB. Have you guys used Simulink? You've seen it at least or not? Has anybody not seen a Simulink model? No, in MATLAB. It's really a way to do block diagrams that do calculations. Like if you have a block in it that would say create a signal f of t, that force signal for our mass, and then you can send it through a product where you would multiply by the mass, and then you could send it through another block if you wanted to, where you could add the number 1 to it. And so the signal that comes out of this block is this signal times m plus 1 and going out. So you can essentially do math as block diagrams. Kind of like the block diagrams that you do in programming, only you don't have programming steps, you just have math operations done in here. So I'm going to show you the MATLAB version of all of the equations of motion that it does automatically for us. But first I have to write the equations up here in vector form, because that's how they're done. All right, so the first 3 force equations you can write back in vector form. Right, we unvectorized them in order to get the x, y, and z equations, but if you jump back a step, we had this. Remember this? It's mass times acceleration. And then you get this extra term because we're in the body fixed axis for the derivative. Yeah, you remember that? There's the gravity vector. There's the aerodynamic, and here's the thrust force. So to do this in MATLAB Simulink, we provide these forces in gravity, and we feed that into an equation that calculates VP dot, and then we integrate that. So divide by m, move the omega stuff over to the other side, and then we're going to integrate this thing in MATLAB. actually simulate. All right, and then we have the moment equations. There's three equations for P dot, Q dot, and R dot, the ones that we looked at here. That's the roll, pitch, and yaw equations. And if you write those in vector form, after we've already figured out what the inertia terms are, right? The IXX, IYY, you rearrange those equations. There's the applied moments. Here's the omega cross I omega that you can write all of those cross product terms in. And then MATLAB integrates this thing. So at every time step, we have to give it the right side, and then it does the integration for us using the Runge-Kutta fourth order method. So I'm going to show you the inside guts of what's called the 6 degree of freedom aerospace block set in MATLAB that does all of this for us automatically because somebody's already programmed to do that. All right, so let me grab the right file. Yeah, hang on, I gotta find the right one here. There's the equation of motion again. So this is the XYZ equations that go into that first vector equation. And then this is the rolling, pitching, yawing. And let's see, I do need to share my screen, don't I? All right, there we go. So there's the force equations that are in that top equation, the VP dot. And then here's the rolling moment equations, or the moment equations, which are in the omega dot equation. This is all the stuff I've been showing you. I just scanned the whole thing in. I need to flip this thing around. Ah, there we go. All right, so let's not look at anything below this line. For right now, so ignore everything down here. So this top does this equation. So let me walk you through. So the forces are this stuff here, the mg plus fa plus ft. So we've got to feed that from outside the block. We've got to say, okay, here's our aerodynamic forces, here's our thrust forces. But then we divide by m here. And so this is a division, this triangle is division. And then we need to add to it the cross product of VP cross omega. So we're going to have to create that over here. So that's what this cross product block does. It takes VB and it crosses it with PQ and R. Let me undo a couple things so that well, I thought I could undo. Let's go back to scratch. Is that okay? There's underneath here is PQ and R, so this is omega here, and this is V velocity. So this is the cross product of omega cross VB. So this block does the cross product. And then well, you're saying, well, how do we get VB? Well, we have to integrate it. And so this block here takes the sum of the cross product and 1 over mass times acceleration. So it's doing this whole right-hand side. And then it calculates VP dot right here. And then this block integrates it. Remember in Laplace, 1 over s is integration? So that's what that's doing. So VB dot is here. It gets integrated, so that's why we get VB or VP. And then we take that and we feed it back here, cross product with the angular velocities, and do it again. So all you do is connect these signals up, and it takes care of doing the integration for us. Where do P, Q, and R come from? They come from the bottom set of equations. And so that's what's done down here. The moments are applied here. We add the moments to negative omega cross I omega. So this part down here does that. And it takes P, Q, and R, does the cross product, feeds it in, multiplied by the inertia matrix here. So that's the I inverse here. And then you integrate it. So it does the integration of V omega dot, and it gets us P, Q, and R. Now, I don't expect you to be able to program this yourself, but I want you to understand that this is exactly what this block set is doing, and it's going to spit out everything you ever wanted to know. It's going to spit out the velocities. It's going to spit out the Euler angles from the kinematic equations. It's going to spit out Earth-fixed coordinates. It's going to spit out Earth-fixed velocity, body-fixed velocities, and it spits out P, Q, and R. So this block integrates the equations of motion in real time. So we will use this block set. I will give it to you in a Simulink diagram later on, and we'll actually simulate a Learjet where we apply an elevator input to it, and you'll apply some inputs to see how well it's trimmed. All right, so what have we covered today? We did the gravity vector in Euler angles. We said we need to do the steady state equations next. So we've taken kind of a side road here to talk about, well, if you don't do the approximations to get the small perturbations in the steady state, you can actually do the full-blown set of equations, but you have to do it on a computer. And we're just integrating one particular input. If you want to analyze the total dynamics, we have to go to the equations and do Laplace transform. All right, next step is we're going to look at the specifics of the steady state equations of motion. But this might be a good time for everybody to stand up, take a 2-minute break. If you want to, go out and get a drink of water. Just be back in 2 minutes. These hour and 20-minute classes, I think, are a little long, so it's always good to stand up for a second. There will be a couple assignments where you need MATLAB. It's available in the lab here. You guys all have student versions? You guys have? Yeah, you can remote into these machines as well. You pirated a version. I won't tell anybody. Oh, the size? Yeah, that. No, just as long. I don't want some weird size. Usually that's for turning in by hand. Because if you turn it in physical copies, I like to stack it up. And if you give me weird size paper, it doesn't work. I guess for scanning, it's not as big a deal. But if you write it on that paper, then all of your scans are uniform and it doesn't get messed up. Yeah, but the line paper is fine. If you want to do an engineering pad or just plain white paper. Okay. Yes, scan your homework, turn it in single PDF file for the entire homework assignment. And well, there's resources. You guys did this last semester, right? Where you used your phone or had your friends copy it in crayon. I don't know. The omega one.
Yeah. So this is the final equation we're supposed to come to. Or we're starting.
That's the starting point.
So K2 is so if I multiply all of this out, then I get K2. Or do I get dot?
Well, this is that I wrote this thing out for you. So you just multiply all this out, multiply this out, add it to that, and you get the final result, this thing here.
Oh, so this is supposed to look like this?
Yeah, you're going to take this and you're going to substitute that, and that into this equation, add it all together to get that.
Oh, so this right here is multiply all of this together, which is the same as this.
Yeah, you should have
There
an
should be an
equal sign there. Yeah.
That's why I was confused.
Okay. All right, let's get back to it. And I think we'll get out of here a little early. All right, so for steady state flight, remember U dot is 0, P dot is 0, W dot is 0, P dot, Q dot, and R dot are 0. So the accelerations are 0, right? Okay, so you're going to do the heavy lifting here. You're going to take the equations of motion that are in your book, and I'm going to put on the screen. And you're going to write them on your sheet of paper. And then we're going to do some stuff to them. So all of these equations, I'm going to give you, how long do you think it's going to take? 5 minutes to write those down? Should we have a race? No, then it'd be real sloppy. So take some care. And one of the reasons I have you write these is the more often you write them, the more you kind of get them stuck in your brain. For better or for worse. I hope you don't wake up in the middle of the night with a nightmare about these equations. Yeah, you're going to be writing the XYZ equations for the force, the 3 rolling moment equations. Don't worry about the kinematic, actually. So it's easier than I was thinking here. Just do the top 6 equations. So when you're done, stand up. There's our winner. Oh, tie here. No, go ahead. If you're done, stand up, just so I know when you're done. Is everybody done? Close to it? We used to have math races in 6th grade when I was in 6th grade. Did I tell you about this? Like long division problems. Sounds like fun, right? Well, it was races. So it was always between me and a guy named Paul Nunley as to who would win, until a kid named Adrian Toole moved into the school district. And he was twice as fast as either of us. And so we kind of gave up. He was just really good. Turns out he went on to major in math. Now still lives in my hometown, bought a big electric company there, owns a big $3 million house up on the hill overlooking the river. So he did good. I don't own a $3 million house, and it definitely does not overlook the Mississippi River. I grew up in Cape Girardeau, which is on the Mississippi. I'm doing okay. I have a nice house near Andover, and sail with a friend on El Dorado Lake, and so that's good. There are not as many trees in Kansas. We know that, right? Okay, how are we doing? So the next thing we're going to do now, you got these written down, and the reason you wrote them is because now we're going to cross out all of those terms I put on the blackboard or the whiteboard. So U dot, V dot, and W dot, knock them out. So do this on your paper, just like I'm doing. P dot's gone, R dot's gone, Q dot's gone, P dot's gone. Did I miss anything? So you just wrote, after you do that, you just wrote the general steady state equations of motion. So you might be saying, well, what about V, R, Q, and P? Should we knock those out too? What's a good question mark color? Yellow, maybe? How about these? Should we knock those out? What if we said W was 0, U was 0, and V was 0? What happens to our airplane? Yeah, all the velocities are 0. We don't generate lift. So that's not a steady state flight condition. That's a static condition. And a death if we were up in the air, right? So we don't knock out that. So make sure that you note that we don't knock out the velocities or P, Q, and R right now. So these are the steady state equations of motion. And they're summarized in your book. So these are equations 1.55 and 1.56 in your book. And these are the equations we'll use to analyze steady state flight to see, well, can we, essentially we're trimming the airplane, right? We're seeing, can we have lift equals weight, thrust equals drag, and if we're in a turn, it becomes more complicated than that. So there's a lot we can do with this. And we've done some of that in 514. We're going to analyze a few more lateral directional cases. We'll look at a one engine in operative condition in a twin engine aircraft where you have to deflect rudder to trim the airplane to keep it from yawing. So we'll analyze that. We'll look at the full 3x3 lateral directional trim problem. There are some special cases that we can do, checking the time here. So the first special case we'll do is rectilinear flight. And so this is cruise. These equations here can handle any steady state flight, but we want to do a cruise flight condition. And so cruise looks like this. He calls it rectilinear flight, which means you're following a straight line, but it's really, I call it the cruise condition, because now we're going to say that the angular rates are 0. Notice I didn't knock out U, V, and W, otherwise we fall out of the sky. So there's no roll rate. There's no pitch rate. And there's no yaw rate. In a minute, we'll add some of those back in, because if we want to do a pull-up, we're going to need some pitch rate, but we don't need roll and yaw. Pull-up's just pitch. If we're doing a steady state banked turn, we won't have any Q, but we'll have some P and R. But for now, we're going to do rectilinear flight, which means we go back to the equations and we knock out more stuff. So now we're going to knock out the P, Q, and R terms. So that means this is gone, this is gone, this is gone, that's gone, that's gone, that's gone, that's gone. Wow, you're saying this is really nice, isn't it? So maybe now you will understand why a lot of analysis is done for steady state cruise flight. Because what's left? It says the total rolling moment is 0. The total pitching moment is 0. Total yawing moment is 0. That's what we call the moment pitch trim equations, right? Total pitching moment is 0. It means the airplane doesn't rotate and pitch. That's what we call pitch trim. Top one would be trim and roll, and this is trim and yaw. The bottom equation for the engine in an operative condition is that we have a huge amount of yawing moment coming from our engine that's still operating out on the wing, and the other one's not. And so we have to generate an aerodynamic yawing moment from the rudder to keep the airplane from yawing, because we have to have the total yawing moment from the engine plus the rudder to be 0. The problem with that is once we start doing that, then we generate some side slip, and the side slip leads to some roll, so we're going to have to throw in some aileron to balance it all out as well. All right, so that's the steady state cruise flight condition. And in fact, I want to switch back to the board. We're going to look at what's left up here in a little more detail, because what are these three equations saying in the cruise flight condition? So are we good with what I have on the screen? You guys have written down what you need? We're good? All right, so what are those three force equations saying? All right, the first one says 0 equals minus mg sine theta plus fa x plus ftx. Oh, by the way, did you notice in the steady state equations there's a 1 put on there? That's how he indicates steady state values in the book. So I apologize totally, I forgot that, but a 1 subscript means steady state. So those steady state equations, the full ones that I showed you, they all, if you notice there are all those 1 subscripts, that's what that means. Okay, so now let's say, well, let's specialize this to level flight, which means we're not climbing or diving, so the pitch angle is 0. Right? So this term is knocked out. This says the thrust plus the aerodynamic X force has to be equal to 0. Well, the aerodynamic X force is the negative of the drag. The drag acts in the negative X direction. FAX is in the forward, so this is negative drag. So if you push it over to the other side, you get thrust equals drag, which is one of the basic equations we can get from just a pure free body diagram for the airplane drawn in steady state. So that's kind of validates what we've done. And how about the Z force equation? So that's what we got when we knocked everything out. And let's say we have wings level. So that means phi is 0. So the cosine is 1. And let's say we're level flight again. So this cosine is 1. And there's no thrust force in the Z direction, typically. So this is aerodynamic force in the Z direction. This is the negative of the lift. Lift is up, Z is down. So what does this say? Negative lift, put it over here. This says lift equals mass times gravity. Lift equals weight. Now notice the full equations before we make these extra special assumptions. So this equation would be good even if we're climbing or diving. We could use this if we're in an airplane and in an F-18 and we're climbing vertically into the sky. That equation works. So does this one. But if we specialize them down to that really simple case that you do in 324, that's what you get. Lift equals weight, thrust equals drag. All right, let's quit there. Next time we'll talk about a level turn and a steady state pull-up.